Okay, good evening, everyone. So I'm going to give a very brief talk today on global sea level fluctuations and uncertainties through a Wilson cycle based on ocean basin volume reconstructions. And this was work that was published last year in Earth Science Reviews and was led by my former PhD student, Nikki Wright, who's now a postdoctoral fellow at ANU. Now, I'm just showing this schematic here, which is taken from Conrad 2013, because I think it's quite a nice illustration of the main components that influence long timescale and long-term sea level change. So if we think about things on the long, on a long timescale, so we're thinking about things at the million-year, tens to hundreds of millions of year timescale, variations in sea level are driven by solid Earth processes. So things like plate tectonics, seafloor spreading, for example, and also mantle dynamics. So dynamic topography would be one example of that. Now, we've looked quite extensively in the past at that plate tectonic component. And this was done quite extensively in our Muller et al. 2008 paper that was published in Science, where we looked at, or we computed a whole bunch of paleo age grids. We converted those to paleo basement depth. We looked at ocean island emplacement, and we looked at sediment thickness and derived these paleobithymetry grids, which we then used to sort of think about what the long-term sea level curve was doing based on these more plate tectonic related factors. So in our new study, the one that Nikki led here, we looked at the components that are circled here in green, and we used the updated plate model of Muller et al. 2019, much of which you would have seen in other presentations that have been presented in this showcase for the BGH. So we used this model to derive paleobithymetry grids. So we made our paleobithymetry grids. But we made some important sort of changes to what we had done previously. So we, of course, looked at the seafloor spreading component, but we also wanted to sort of understand what the effect of, or what the influence of back arc basins are on the seafloor spreading record, and therefore on the component to sea level change. So we looked at the influence of these back arc basins and marginal seas, particularly because they're quite difficult to capture in older reconstructions. We have a pretty good idea of what they're like, in the last few tens of millions of years, but yet we don't really incorporate many of those as we move back in time because we just don't have the seafloor spreading record. So we looked at trying to understand what their influence is and trying to put that back into our resultant sea level curve. We also explored the effect of several ranges of spreading asymmetry. So when we derive our age grids for periods of time where we don't have much information, we just assume spreading symmetry. But we looked at, well, let's have a look and see what the influence would be if we assume certain percentages of spreading asymmetry. And let's just add a reasonable component based on present day observations of a component of spreading asymmetry to our sea level as well. So we looked at various different types of these seafloor spreading type parameters. We also looked at large igneous provinces, but we improved our workflow by looking at the swell component of these large igneous provinces, and also reconstructed the conjugate lip segments. We included a previously published an improved sediment thickness prediction, which was published by Adriana a few years ago. And that looked at sort of the mean distance to the passive margins, but it also looked at the ocean basins as individually rather than creating a global relationship. So those were incorporated, and we also looked at changes in continental area, and this was mainly done by focusing in on increases in areas based on continental stretching and passive margin development. So in this study, we didn't look at any of the mantle components. We just focused in on those more plate tectonic related components. So we didn't look at things like dynamic topography. We didn't look at things like water cycling, and we also didn't look at glacial effects. And here I'll just show, and I've embedded this from YouTube just to highlight the fact that we've got the Earthbite YouTube channel, which has lots of good resources for many of the papers that we've published over the years. And this is just showing the resultant paleobathymetry that we have, which takes into account the depth to basement from the age grids, looking at those large igneous provinces, sediment thickness, to come up with the paleobathymetry. So what's not shown here are the passive margin reconstructions that we've done as well. So you can see that generally, as we're moving forward in time, we're getting generally deeper ocean floor compared to what we've had in the earliest Mesozoic time period. Now, in the interest of time, I'm not going to go through each component and explain to you how we computed each component and what their individual influences are. So instead, I just wanted to show you this summary graph. So this shows time on the x-axis and sea level on the y-axis. And I'll just get you to focus in on that red line there. That red line is showing our traditional method. So this, or traditional model based on our traditional method. So this is looking at depth to basement. It's looking at our improved sediment thickness and also our improved lip, our lip workflow as well. And so what we can see here, as in this red line, this traditional model, is that we can see a really quite significant drop off, pre-Cretaceous times in sea level. Now, if I focus you in on the refined model, which is this black line, so this is where we have also included components that we just never took into account before. So things like what's the area change related to and including passive margins. So if we include that area change, well, how will that influence sea level? What component would that add to sea level? Also, we estimated lips for times when we don't have any preserved lips. And so we've added that component to that sea level curve as well. And then also the back arc estimate. So we make an estimate of back arc basin influence because during this time period, particularly in these pre-Cretaceous times, we really don't have enough back arc basins in our models just based on a lack of evidence. Preserved evidence of them. So what would that component be? And then we derive this refined model of sea level. And if we wanted to compare these with other sea level curves, so I've just plotted here the sea level curves that are based on plate tectonic models. So you can see various ones that are plotted here, including some of our own. And then I've plotted here ones that are based on stratigraphic methods. And I know that these aren't strictly stratigraphic models because I do know, for example, Hark, for example, has a seafloor spreading component to his curve, but they're mainly based on these stratigraphic methods. And then we can plot our ones on top there. So we can see the red line, which is the red line previously, shows that traditional method. So we can see that that is not really quite a good estimate, particularly for those, as I said before, pre-Cretaceous times. But when we look at our refined model, which is in black here, well, we can see that we're getting better matches with previously published models. So we can see that by incorporating these components, we're actually getting a much better idea of what that long-term sea level curve looked like. So just a very brief summary. We've got new paleobathymetry grids, which are based on the recent reconstruction of Muller et al. 2019. And we've got all these refinements to our workflow. And we can see that plate tectonic factors such as back arc basins, thinking about spreading asymmetry and passive margins, and also sediment thickness are really the most important things to consider in paleobathymetry reconstructions. And when we incorporate these factors, we do find that we get sea level change by up to about 280 metres since the Jurassic, so quite significant. And the other important message is that with the long-term sea level trends that we find are robust. So irrespective of whether we're changing and adjusting our plate model as we go, the long-term sea level trends that we've been observing since 2008 are there, and they're quite robust. If you wanted more information about any of the details, which I've completely skipped over in this presentation, please just send me or Nikki an email and we'll be very happy to go through things with you or to share any of the workflows. Thank you.